The explosion of a starship in the upper atmosphere would cause holes in the ionosphere. Welcome back to my channel. Today, I'm presenting this new video where we return to talk about SpaceX, the great startup now known to everyone by Elon Musk. Let's get started.
T-minus 10, 9, 8, 7, 6, 5. We have propane ready to start. 2, 1. Here. Booster ignition. Stall.
Today we're going to talk about something really interesting, a research study published in Geophysical Research Letters. And this study shows how the Starship from its second test flight, which took place in 2023, could have significant effects on the atmosphere. Researchers have explored how such high-energy events can impact the ionosphere and even potentially cause disruptions that affect satellite communication and GPS systems. Let's dive into the details of this fascinating research and see what implications it has for the future of space travel. In that case, after the Starship had ascended, just 8 minutes later, the Starship exploded at about 150 kilometers above the surface, causing a hole in the ionosphere. But what is it? The ionosphere is a region of the Earth's atmosphere located between about 30 and 1,000 kilometers in altitude, composed of electrically charged particles, ions, and electrons. This area is important for several reasons. Radio wave conduction. The ionosphere reflects certain radio frequencies, enabling long-distance communication, especially for short-wave transmissions. Without the ionosphere, many radio communications might not reach from one continent to another. Protection from solar radiation. The ionosphere helps shield the Earth from harmful solar radiation, such as ultraviolet rays and energetic particles from the sun, interference with satellites and navigation. The presence of ions and electrons in the ionosphere can affect signals from satellites, such as those used for GPS, causing errors in their accuracy. Aurora borealis and australis. Auroras are light phenomena visible in polar regions caused by the interaction between the solar wind and the gases in the ionosphere. But what is it? The ionosphere is a region of the Earth's atmosphere located between about 30 and 1,000 kilometers in altitude, composed of electrically charged particles, ions, and electrons. This area is important for several reasons. Radio wave conduction. The ionosphere reflects certain radio frequencies, enabling long-distance communication, especially for short-wave transmissions. Without the ionosphere, many radio communications might not reach from one continent to another. Protection from solar radiation. The ionosphere helps shield the Earth from harmful solar radiation, such as ultraviolet rays and energetic particles from the sun. Interference with satellites and navigation. The presence of ions and electrons in the ionosphere can affect signals from satellites, such as those used for GPS, causing errors in their accuracy. Aurora borealis and australis. Auroras are light phenomena visible in polar regions, caused by the interaction between the solar wind and the gases in the ionosphere. Marconi's achievement was a groundbreaking moment in communication history as it demonstrated the potential of long-distance wireless transmission. At the time, scientists did not fully understand how the ionosphere worked, but Marconi instinctively used its reflective properties to transmit signals across the Atlantic. His success paved the way for the development of global radio networks and revolutionized communication technology. This marked the beginning of a new era in telecommunications, leading to the widespread use of radio and later satellite communication. So, the so-called shortwave radio waves bounce off the ionosphere.
And it is the ionosphere that, for example, is used to extend the range of shortwave radio communications. However, the ionosphere is also crossed by radio signals, such as those coming from satellites like GPS signals. If you alter the local structure of the ionosphere, obviously, all these communications will be affected.
The ionosphere is not just a passive layer. It is constantly influenced by solar activity, including solar flares and geomagnetic storms, which can also disrupt communication and navigation systems. For instance, these disturbances can cause signal degradation, delays, or even complete blackouts for GPS systems. As a result, researchers and engineers must account for ionospheric variations when designing systems that rely on satellite communication or navigation. In the context of space exploration, any large explosion or high-energy event, such as a rocket launch or an explosion like the one involving Starship, could cause localized disturbances in the ionosphere, leading to temporary disruptions in communication or navigation systems, especially those that depend on precise timing and positioning. This is why studying the ionosphere and understanding its behavior is critical for ensuring the reliability of modern communication technologies.
Now, what happened is that Russian and French researchers analyzed data from 2,500 GNSS stations in North America and the Caribbean. For those who may not know, GNSS stands for Global Navigation Satellite System, which is a network of satellites that provide geospatial positioning data. This includes systems like GPS, Global Positioning System, used for precise location tracking and navigation. These researchers focused on studying the effects of disruptions to the ionosphere, especially in the wake of large space events such as rocket launches or explosions. By analyzing GNSS data, they were able to observe how ionospheric disturbances, like the ones caused by the Starship explosion, could lead to errors or interruptions in navigation signals, affecting both everyday users and critical infrastructure. This research helps improve our understanding of how the ionosphere behaves during such events and provides important insights into how to better mitigate the effects on satellite systems. By collecting data from such a large number of stations, they were able to create a more comprehensive picture of the ionospheric impacts across a broad region, providing valuable information for future space missions and satellite-based technologies.
So they found that by analyzing two radio frequencies emitted by satellites, and especially depending on the speed at which these radio waves traveled through the atmosphere above the Gulf of Yucatan, they tried to understand how a shock wave had formed from the explosion of the Starship's second test flight. This explosion displaced free electrons within the atmosphere, altering the percentage of their presence within that layer.
The researchers used the data to track how the shockwave from the explosion affected the ionospheric conditions, specifically how it changed the concentration of electrons in the ionosphere. These changes in electron density could cause signal delays, as the speed of radio waves depends on the density of the ionospheric particles they pass through. This phenomenon could lead to navigation errors or disruptions in satellite communications, as seen in previous studies of similar events. By studying the wave's propagation and the variations in the ionosphere's electron density, they were able to estimate the impact of such explosions on satellite-based systems. This research underscores the need for more detailed models of the ionosphere's behavior, especially during high-energy events like rocket launches or explosions, to predict and prevent possible communication failures in the future.
It was as if that area had been hit by a localized solar storm. In reality, they began to notice the anomaly initially when the shockwave from the explosion changed the composition of the ionosphere, first within a 1,000 kilometer radius, and then gradually it expanded up to 2,000 kilometers, and this is something significant. So in 2018, several studies analyzed the effect of Falcon 9 rocket launches on the Earth's ionosphere. In particular, the launch of the Formosat 5 satellite on August 24, 2017, generated an extraordinary shockwave, creating an ionospheric depression about 900 kilometers in diameter. This phenomenon caused slight disturbances in GPS navigation systems with temporary errors of about 1 meter. The research highlighted that the combination of a particularly light payload, 475 kilograms, and an almost vertical flight trajectory contributed to the formation of a large circular shockwave. This launch approach differed from traditional V-shaped trajectories, amplifying the impact on the ionosphere. A numerical analysis simulated the ionospheric depletions resulting from rocket launches using a general circulation model. The simulations showed that the Formosat 5 launch caused a more extensive and longer-lasting ionospheric depletion compared to the Jason 3 launch, in line with experimental observations. These studies emphasize the importance of understanding the effects of rocket launches, such as Falcon 9 on the ionosphere, as such events can influence satellite communications and global navigation.
The Falcon 9 is a partially reusable rocket developed and manufactured by SpaceX, the private space company founded by Elon Musk. It is one of the most successful and cost-effective rockets in operation today, and is used primarily for launching satellites, cargo, and crew into space. Here are some key points about Falcon 9.
Design and reusability. The Falcon 9 is designed with reusability in mind. Its first stage, the lower portion of the rocket, can land back on Earth after launch and be refurbished for future missions. This reusability significantly reduces the cost of access to space. The first stage is powered by Merlin engines which run on rocket-grade kerosene and liquid oxygen, RP-1 LOX. The second stage is powered by the Raptor engine, fueled by liquid oxygen and liquid methane for future long-duration missions to Mars, for instance.
A very important note regarding the orbit burn maneuver is atmospheric pollution. This is something that we should be paying attention to, although it is not always considered a major issue. Every time we launch a rocket with a specific type of propellant, we chemically alter the ionosphere for a couple of hours. However, if the rocket explodes, we modify the ionosphere, not just chemically, but also mechanically.
The explosion causes a shockwave that disturbs the ionosphere, pushing electrons and other particles out of place, which can lead to temporary gaps or irregularities in the ionospheric layer. This mechanical alteration could have a more lasting effect compared to just a chemical change. Such events might interfere with satellite communication, navigation systems, or even weather forecasting, which rely heavily on the stable behavior of the ionosphere.
So it's crucial to consider these factors when planning space missions, especially when testing new technologies or conducting launches that could impact the atmosphere on a larger scale. While rocket launches are essential for scientific and commercial progress, understanding the broader environmental and atmospheric consequences of such activities is key to minimizing their negative effects. I hope you enjoyed these slightly different news. See you in the next video.